Hey everyone, it's Mrs. Cat, and today I'm here to talk about the mole. This is a unit of measurement that we use in chemistry. It is not a small animal that digs under the ground. I mean, it is, but that's not what we're talking about today. So we'll dive right into it. A couple questions that are going to help us intro what a mole actually is. And that first question is, what chemists use to represent how much of a substance they have? Okay, focus here is how much. And that unit of measurement is going to be measuring mass, which we measure in grams, right? Kilograms, other metric base units or metric units of mass can apply here. But if we want to know how many atoms or how many molecules of a substance we have, this is where we're going to use moles. Okay. Moles is the name as well as the actual unit. Our abbreviation for this is not a very major abbreviation. It's MOL. And then the symbol that we use for moles, we've actually already used, and that is the letter N. We saw this with our gas unit. This is going to be our measure of amount of substance. So we're going to define moles in a few different ways. First of which is where this actual value and measurement originates from. And that is from the number of atoms of carbon in 12 grams of carbon-12. This is an isotope of carbon, which just means it's a type of carbon. We're going to get a little bit more into that very soon, but that's where this really comes from. Now, we are actually going to use this as not just based on carbon-12, because that's not going to help us for anything but carbon-12, but we're going to really say that this is the number of particles and this particle is going to be, the name of it is going to be dependent on what we're looking at. Just like we've been looking at so far this year, a particle could be an atom, it could be a molecule, if we have a compound. Sometimes we're going to also call those formula units. And then we're going to also talk about particles that are called ions. So anytime you're looking for the number of those things, we're going to use this unit of the mole. Okay. Now, the actual number of particles that we have is really, really large. Okay, so give me a second here to write this out for us. Okay, let me see here. 2, 3, 10, 11, 12, 13, 14, 21, 23. Okay, let me double check here. Make sure that I have this. Now, I promise this is going to be the only time that you have to write this number out in its entirety. So 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 17, 18, 19, 20, 21, 22, 23. Great. Okay. So 6.0 or 6022 followed by 21, 20. I don't know. We should have a total of 24 digits here. This is our number of particles. Now, it's kind of ridiculous, right, to write all that out. But I do want us to look at it in its entirety, not in scientific notation at this point, so we can see how big this number actually is, right? Really, really big number of particles. Like I said, this is the only time you'll actually have to write this out as is. We will obviously use scientific notation for this every other time from now on. That's going to be 6.022 times 10 to the 23rd power, and that's our number of particles. Now, there is a special name for this particle number, and that is Avogadro's number. Now, we've heard of Avogadro before when we talked about Unit 4 and Avogadro's hypothesis, but Avogadro was also important in determining this number of particles in the unit of the mole. Okay, so we can summarize all of this in a for every statement, which we will do now. we can say that for every 1 mole of a substance, there are 6.022 times 10 to the 23rd particles. Okay, so this may not really mean a whole lot right now, and that's okay, but we are going to take a look at this as an example using something that you do really know about, which is a dozen. Okay, the mole is a unit similar to a dozen. Doesn't matter what it is that you're talking about, what it is that you're trying to count. Okay, if you have a dozen of something, it's always going to be 12, right? So we know that 1 dozen equals 12 items. Okay, in this case, we're going to look at a dozen eggs. Okay, so 12 items. Okay, in this case, this is eggs, right? If we're talking about a mole of something, it's a similar relationship. A mole of something is going to be 6.022 times 10 to the 23rd items. In our case, since we're talking about chemistry and substances, where that item is going to be a particle. Okay, so we're going to use this to convert between our units, just like we've been doing all year long, using proportional reasoning. So I want to know how many eggs there are in 5 dozen. So I'm going to set up a proportion to help me do this. Okay. Now, I always like to make my X value on top. So I'm going to know X number of eggs in 5 dozen. And I'm going to set that equal to my proportion that I do know, which is that there are 12 eggs. Whoops, helps if I spell it correctly. In 1 dozen. Okay, so now we just solve for X. We're going to cross multiply, okay, and divide if necessary. In this case, all we're going to need to do is take 5 times 12, which is going to give us 60 eggs. Okay, so there's our simple example. Okay, we can use the unit of the mole in a similar fashion. Okay, so we're going to do an example here where we're going to convert from atoms, molecules, ions, any type of particle. Okay, this is going to be what this example is going to look like. So if I want to know how many atoms there are in a mole, we're going to use that conversion factor of 1 mole equals 6.022 times 10 to the 23rd particles. Okay, and remember, particles can be atoms, molecules, formula units, ions. Just the name of the particle type depends on what type of substance we're looking at. Okay, we got 3 moles of a substance, and we want to know how many molecules there are. So we're just going to set this up just like we did our egg conversion. I want to know how many molecules. Now, I'm going to abbreviate molecules MLC just because I don't want to write it all out. Okay, so X molecules in 3 moles. Looks like I made my line a little too long. And then I can set this up as, okay, I know that 1 mole is going to be 6.022 times 10 to the 23rd molecules. Now, just as a reminder, when you are inputting numbers in scientific notation into your calculator, make sure that you are using your calculator's version of scientific notation input. Okay, that's going to either be EE times 10 to the X. Make sure that you know how to use that on your own calculator. Please do not do 10 caret and then 23, or especially times 10 caret 23, because you're going to wind up with an improper number of powers of 10. So I'm going to talk you through exactly what I would put into my calculator here. I'm going to cross multiply. Again, in this case, we don't need to divide to solve. So what I'm going to do to find the number of molecules in 3 moles is take 3 times 6.022 on my own calculator. I have an EE button, okay, and that gives me a little times 10 to the in my calculator, and then I'll put in 23. Okay. When I do this, this is the answer that you'll get in your calculator, or you should. So make sure this is what you get. 1.8066 times 10 to the 24th. Okay. And this is molecules. This is not going to be my final answer yet because this is not rounded to the correct number of sig figs. Okay, we're going to use 3 moles as our least number of sig figs. So we're going to round to 1. We're going to make this 2 times 10 to the 24th molecules. Okay, now this is great, except for it's really not reasonable for us to actually count particles. So in order to make that a little easier on us, what we have to do is consider mass and how mass can play into our conversions between moles and other units. So the basis of the atomic mass unit, which when you are looking on a periodic table, that's what you're going to want to, that's the value you'll see for mass on the periodic table. This is also based on carbon-12. Okay, again, we're also going to get into this a little bit more detailed a little later on. So the basis of the atomic mass unit is that it's 1/12 of the atomic mass of carbon-12. Okay, again, that's just a type of carbon. We'll get into talking more specifically about that very soon. Okay, again, basis of Avogadro's number is also from carbon-12, and that is number of atoms. Let's actually say number of carbon atoms in 12 grams of carbon-12. Okay, so we can use these two relationships and the fact that they're both based on carbon-12 to make a conclusion. Okay, and that is that the atomic mass on the periodic table also gives the mass of 1 mole of an element but this time the unit is in grams. Okay, this is big. This is super important. Okay, I'm actually going to also highlight this. Okay, maybe you want to do the same. Maybe you want to put a star or something next to it, put a box around it. Okay, but that is a really important conclusion. Okay, this is going to allow us to find the molar mass of a substance. That's just the mass of a mole in grams. Okay, 1 mole of a substance. Now, we're going to use the periodic table to help us find these values. Okay, we have standard periodic table that we will use in our course. If you have a physical copy of it, it's likely probably printed on blue. But the periodic table you're going to want to use for your atomic mass / molar mass values is going to be the one at the top that looks like this. Okay, if you have a digital copy of it, it's going to be exactly the same. Okay, so in order to get the molar mass of an element, all we're going to do is look at that periodic table, find the atomic mass from the periodic table, and I'm going to abbreviate periodic table PT, and then we just put this in a unit of grams per mole. In order to find the mass of compounds of from the periodic table, we're going to just add up the mass of all atoms and again, this is going to be in grams per mole. Okay, so we're going to look at these molar masses, which will then serve as conversion factors. So let us go from grams of a substance into moles or from moles into grams. Okay, so if we look for the molar mass of calcium, this is an element. It's a monatomic element. So all we're going to do is look up its value from the periodic table. Okay, if you find that, it's going to be 40.08 is the mass value listed on the periodic table. And we're going to put this as grams per mole. Okay, so if we're going to write that as a proportion, that would be 40, having some syncing issues here. Let's try this again. 40.08 grams of calcium in 1 mole of calcium. Okay, these are always for 1 mole. Okay, if we're looking at chlorine, elemental chlorine is diatomic, so we've got 2 atoms of chlorine that we need to take into account. So we're going to find the mass on the periodic table and we're going to multiply it by 2. Okay, molar mass of chlorine, 1 atom, is 35.45, and that I get from the periodic table. Okay, so this is going to be, let's actually go ahead and put a unit on that, grams per mole. So my molar mass of Cl2 is going to be 70.90 grams per mole for Cl2. Okay, so looking at the molar mass of a compound, in this case CaCl2, we're going to just take exactly what we have. 1 calcium plus 2 chlorines to get the total mass of this compound. Now, since we already have the individual pieces of these, I'm going to just go ahead and add those up, which is 40.08 grams per mole for the calcium and 70.90 grams per mole for the 2 chlorines. Okay, this is going to be 110.98 grams per mole for CaCl2. Okay, now if I hadn't done this individually for the calcium and the Cl2 to begin with, what I would have done was to add up 2 times 35.45. Okay, it's going to get me the same thing. Okay, great. So now that we have the ability to determine the molar mass, and we know that we're going to use these as conversion factors, then we can convert into or from moles to grams. Okay, so we're going to convert between these. We're just going to look at 2 of these examples. I'm going to look at, let's see here. Let's look at number 2 and number 4. Okay, and we're going to just convert from one to the other. So if we're given moles, we'll convert to grams. If we're given grams, we'll convert to moles. But I actually want to start out by finding the molar mass of each of these, and then we can go from there. Okay, so I'm going to do molar masses in green. I've got molar mass of H2. This is diatomic hydrogen. So I'm going to take 2 times the mass of hydrogen from the periodic table. It's the first element on there. It has a mass of 1.01 grams per mole. And so this is going to be 2.02 grams per mole of H2. Okay, fantastic. Okay, like I said, I'm just going to go ahead and go on to that conversion factor for the second example we'll do, which is number 4. And this is CuSO4. So we've got more pieces here for our compound. So we want to start by looking up Cu, that's copper. Find it on the periodic table. Its mass is 63.55. Okay, plus 1 sulfur. Okay, S, that's 32.07. And then I've got 4 oxygens. So I want to add those all up together. Those are each 16.00 grams in 1 mole of oxygen atoms. Okay, and then I can add all these up together. Some of these elements we'll use a lot, and you'll probably just remember their masses from the periodic table, but please know that you will always have a periodic table available to you. You're not going to be expected to memorize these. Okay, so let's add these all up. 63.55 plus 32.07 plus 4 times 16 should give us a total mass of 159.62 grams per mole. And again, this is for CuSO4. Okay, now that I've got my conversion factors taken care of, let's go back and do these examples. Okay, so we've got moles of H2 given to us, so we're going to convert into grams. So I want to find the number of grams, maybe. There we go. Grams of hydrogen, H2, there are in 2.45 moles of H2. Okay, notice how I'm keeping the units and the substance, whatever our element or compound is that we're looking at, when I'm putting my units on here. That's going to be important later on, that we're keeping track not just of the units, but also of what substance we're looking at. Okay, molar mass, match up your units so that they are on the correct part of our proportion. Okay, we want grams on top, we want moles on bottom so that they match. Okay, this is for every 1 mole. There's going to be 2.02 grams of hydrogen. Okay, so in this case, cross multiply, that's all we need to do to find our number of moles. I'm going to go, or excuse me, grams. I get 4.949, but I want to round to 3 sig figs because I was given 3 from the moles of H2. Okay, so that should be 4.95. And the unit here is grams of H2. Okay. All right, great. Okay. Finish that up, put a nice little box around it. Okay, if we're going to go the opposite direction, we're still going to set things up in a similar way. Okay, but this time, if I'm given grams, I want to go into moles. So I'm searching for the moles of CuSO4. There are in 0.25 grams. Okay. So I'm going to use that conversion factor of molar mass and set this up so that my units are in the same places on both sides of my proportion. So I know it's always going to be for 1 mole, and this is CuSO4. Okay, and then my mass is 159.62 grams. Okay, this time I'm going to have to cross multiply and then divide. Okay, 0.25 times 1 is just 0.25. X times 159.62. I want to divide by that 159.62 to get X by itself. So when I do that, hopefully, I'm going to get a pretty small number. I'm going to go ahead and put this in scientific notation. But I get 0.001566 and then a series of other numbers. I'm going to put it both in normal standard notation and scientific. So if I round this to 2 sig figs, I'm going to make this 0.0016 moles of CuSO4. If you want to write that in scientific notation, fantastic. Okay, I would make that 1.6 times 10 to the negative 3rd moles CuSO4. Same value, just a different way of representing it. Okay, so that's how we can go and convert between either particles and moles and back again, or like we just looked at here, moles and grams and back again.